Hello and welcome to today's physics lecture, wherein we shall be discussing the M or the magnetic dipole moment of a revolving electron, right? So for example, we take that like over here, this is the electron and the charge of the electron is say E minus. As we know that the charge of an electron is always negative. Now this electron is revolving in a definite circle, because we know that electrons actually do revolve around a definite orbit, right? And according to the Bohr's theory, we know that actually the electron do revolve around an orbit which has an integral multiple of value of say h divided by 2 pi. But let us come to this concept afterwards. First of all, this E or the electron is revolving. So this will revolve in say a path like this. This is a plane, right? The electron is revolving say in this direction. Then as we know from current and electricity that the direction in which actually electron makes its path, the current that is over there flowing will just be on the opposite direction, right? So we can say that the I that is being produced over here will be along this say path, and the direction of the I will be like this. This is I, because from current electricity we know that actually I flows from the positive terminal of the battery to the negative terminal of the battery in a circuit, right? Whereas the electrons, as being the negative, they actually are on the negative side and they are attracted towards the positive. So the electron moves from the negative end to the positive, whereas we know that the I actually moves from the positive end to the negative end. So from that we can deduce the conclusion that if the electron is revolving say counterclockwise direction, in that circumstances the I that will be produced, that will be in the clockwise direction. Now over here, if we do wish to establish a relation between I and E, we know that I is equals to the rate of flow of say charge. Over here, the charge is electron and only obviously one electron. So we can write over here that I is equal to E divided by the time. Now over here, what will be the time? The time over here will be that how much time this electron from this particular point revolves around this specific orbit to come again at that point. And that time is basically known as the time period of one revolution. Now, so for example, this electron is revolving around with an angular velocity, say omega. So omega is the angular velocity with which the electron revolves. Then we know that omega is equals to 2 pi divided by t, where this t is actually the time period which is equal to complete one revolution. So you can write that t is equals to the time period. And obviously this t or the time period over here shall be in the denominator to find out the amount of current over here that is associated. So we can see that I is equals to E divided by G. Now we know that this equation could be transformed as E divided by, if we replace this T, capital T, as per this equation, we will get T as equals to 2 pi divided by omega, right? So it will be 2 pi divided by omega, which means that E omega divided by 2 pi. As we know that the denominator of the denominator is basically the numerator, right? Now let us say that this is the first equation. Now we are actually supposed to find out the magnetic dipole moment and know the value of this current. Then why are we actually interested in finding out the sign? Because we know that to find out the magnetic dipole moment, or M, the M expression or the formula of this M is simply equals to I multiplied by the area, right? So if we wish to find out M, then obviously the value of I will be this one, the E omega divided by 2 pi. So let us write that, multiplied by the area. Now what will be the area actually? The area of this circle. Say for example this orbit is located at a distance of r, right? So the area over here being enclosed by this, say, moving electron or the revolving electron or this charge will simply be equals to pi r square multiplied by pi r square. And if we do observe closely, this pi will cancel out this pi, so the expression remains as E omega r square divided by 2. Now let us multiply and divide this expression by the mass of the electron. So multiplied by mass of the electron and divided by the mass of the electron, where ME is equals to simply mass of electron, right? So we can find this expression of M as equals to E divided by 2 multiplied by the mass of this electron multiplied by mass of the electron multiplied by omega r square. Now, if you could actually remember the rotational dynamics, a body of mass ME revolving with an angular velocity of omega, and over there the radius of this circle of revolution is equals to r. So ME multiplied by omega multiplied by the square of this radius will simply be equal to the angular momentum. And as we know that the angular momentum is actually denoted by capital L, so the capital L will be the angular momentum of this particular electron which is revolving around this orbit of, say, this green path, right? So we can replace this particular term as L. So hence we can write as M equals to E divided by 2 mass of electron multiplied by the angular momentum of this particular electron revolving around in this definite orbit. around the nucleus. Over here, there will be the nucleus, which consists of the protons and the neutrons, as we all know. So here comes the expression for the magnitude of this M, or the magnetic dipole moment. Now if we wish to find out the direction, obviously we know that to find out the direction of this L, or this angular momentum of electron, we could simply use our right hand, the Maxwell's right hand thumb rule, or the corkscrew rule. Let us keep the fingers curled around the direction of the movement of the electron, or the revolving of the electron, so we can see that actually the L is in this direction. Because if we curl our fingers along the direction of the movement of the electrons, our thumb will actually show the direction of the angular momentum, which is directed towards the reader. Right? Now, if we wish to find out that what will be the direction of this M, of the magnetic dipole moment, which obviously is a vector quantity, over here what we could do is that we know that the charge over an electron is actually and basically negative. So let us put it as the vector M will simply be equals to minus of the charge of an electron divided by twice the mass of the electron multiplied by this vector of angular momentum. So in this particular expression, we could actually find out that this magnetic dipole moment is negative in direction of this L. This is in the vector form. This was its magnitude, irrespective of the E, that whether it is negative or positive, but this direction actually indicates that in what direction it should be. So, by the use of the vectors, we can understand that this M vector will actually be in the opposite direction of this L. So we can now say that if L is in this direction, obviously the M will certainly be in this direction. Right? So, to find out the length, let us take the help of the right hand thumb rule. Along the direction of the movement of E, we shall find it out, that it is towards the reader. And if we do wish to find out the direction of this magnetic dipole moment, let us check the flow of the current over here. With the help of the right hand thumb rule, we shall see that the curling of the fingers along the direction of I, then the pointing of the thumb is actually inside this paper or the whiteboard, or this direction of M is actually away from the reader. Right? Now, according to Bohr's theory, it states that in Bohr's theory that actually this particular electron is being allowed to revolve around a particular orbit, right? And if it happens as such, then the angular momentum will simply be equal to the integral value of h divided by 2 pi, where h is known as the Planck's constant. So let us see, if we are telling that L over here is equal to the integral value of h divided by 2 pi, then obviously the expression shall look like L is equals to h divided by 2 pi, where h is basically the Planck's constant, and we know that the value of L is simply equals to mass of the electron multiplied by omega r square. So hence we can write it as mass of electron multiplied by omega r square is simply equals to h divided by 2 pi. Right? Now it has been told in the Bohr's theory that this angular momentum will be an integral multiple of h divided by 2 pi, which means that we need to multiply it by n. Over here also it needed to be multiplied by n, where n may be regarded as the integral values is equals to 1, 2, 3, like this. It will be integral value, not any fractional value, say, of n equals to 1.5 or n equals to 2.75, not like that. Right? As we know, like in the case of the quantization of charge, likewise the n will be treated only as integral values. Right? So over from this expression now, if we know that this expression is equal to this, so we can keep this one as equals to this, right? So if we wish to find out the m, or the magnetic dipole moment, we can find it out as the magnetic dipole moment is equals to E divided by twice of the mass of the electron multiplied by this angular momentum. Now will be replaced by nh divided by 2 pi multiplied by nh divided by 2 pi. So we can write m as equals to ENH divided by 4 pi ME. Right? This is over here. And another expression for the magnetic dipole moment in terms of not this omega, not this r, in terms of the charge of an electron, n, I mean the integral value for which it has been considered, either 1 or 2 or 3 or something like this, because as it is dependent on the orbit that in which shell this electron is revolving, either in K shell, L shell, M shell, N shell, whatever may be, then the Planck's constant divided by 4 pi and the mass of the electron. Now, say for example, in the least case, we take the value of n is equals to 1, because the value of n over here cannot be 0, because we have not found out any as such atom where the electron is actually on the nucleus. Because if it had been on the nucleus or in the nucleus the electron, then only the n would have been 0. But this is not the case, so the minimum value of the n could be taken as 1. So if we take the minimum value of n as equals to 1, then the value of m, or the magnetic dipole moment, what we shall be finding out is known as 1 Bohr magneton. Right? So, replacing n equals to 1 at that point of time, the m which is found out is 1 Bohr magneton. Right? Now we know that what is the charge of one electron we know over here that n is equal to 1. We know the value of the Planck's constant, and also we know the value of the mass of an electron. So we can obviously find out the value of one Bohr magneton, right? So, one Bohr magneton, if we are going to put and replace these values, we shall be finding it out as 9.2 multiplied by 10 to the power minus 24 ampere meter square. Right? Thank you.